Okay, looks like we're live now. Hopefully everything is recording properly. I'm also going to record my desktop another way, just to make sure we don't have any of the problems that we had last time. All right. We'll be starting in just a couple of minutes here. Just getting a few things set up. All right. We're just about ready to get going now. Okay, it's 10 o'clock. I think we'll go ahead and try and get started. Hopefully everyone is able to see my shared desktop. I'm using a couple of different technologies for this little demonstration today. We're using Hangouts on Air, which is broadcasting live, and that's hopefully how you're able to watch it now. You can type questions into Hangouts on Air directly, and they should show up on my screen here, which I will check from time to time and see if anyone's got any questions to ask. Now, if you start watching a little after 10 o'clock, a little after the initial broadcast started, you'll see it from the beginning, so you'll actually be a few minutes behind. And then if you ask questions, I won't see them immediately, but I'll hopefully see them before the broadcast ends. I'm also using ScreenFlow to record this on my Mac, just in case something goes wrong, as it has in the past with this automatic recording that Hangouts on Air provides. And finally, I'm going to be using Turbo VNC and Virtual GL, which allow me to display my Linux desktop from my Macintosh. I wanted to use a slightly more powerful machine today than I did in some of my previous demonstrations. So we'll have to see if the combination of all of these different technologies works smoothly or not, but hopefully everything will go all right. All right, so the idea behind today's little demonstration is we finally released EMAN2.1 a few days ago, and I had previously done a demonstration showing the 1 hour to sub-nanometer resolution using the traditional GROW-EL dataset that we've used for EMAN demonstrations for the last 10 years or something like that. That was sort of a rush demo to try and get through everything we could get through in about an hour. Today I want to start going through a project a little bit more gradually. I'll take my time. We'll actually look at the data carefully. We won't get through the whole thing in today's roughly 1 hour session, but we'll get started on things, and then I'll do additional sessions over the next few weeks, and we'll try and go through sort of the full tutorial. So I'm going to use a different data set today instead of the GROW-EL data set that we've used in the past, and I'm going to use one that I've publicly available data set from the public archive that the EMDB has started providing. So I'm going to go back here and show you this page. So this is Empire. This is the cryo-EM raw data database. This is different than the database where you store the EM data bank where structures are stored. This stores all of the raw data that went into the structures that were deposited into the EMDB. Now, this is only a small subset of the structures. People have to volunteer to provide their data here. Only a few people have so far, and I don't think they even want all of the data sets that are available. The idea is to have some representative data sets here that people can play with in processing. And I looked through this list, and I decided we'd try something a little different. Well, I don't want to do ROEL because it's got high symmetry. We've done it 1,000 times before. I don't want to do ribosome because everyone's seen ribosome demonstrations before. So I thought I would try this beta-galactosidase structure, which was solved at 3.2 angstroms by Sriram Subramanian's group. Now, there's another beta-galactosidase structure, it looks like, that's coming out from the MRC, but that one hasn't been fully deposited yet. So we'll go with this one. Now, this is not going to be a 2-day demo or something, so I don't want to try and process all 109 gigabytes of these average movie frames. What I'm going to do is I'm going to pick a small subset of this data, and we'll process that. We're not going to get to 3.2 angstroms that way. We're going to get to slightly worse resolution, but we'll be able to get through it in a reasonable amount of time. I've already downloaded the data because downloading 109 gigabytes, as you can imagine, takes a little bit of time. So let's take a look here. I've set up just an empty directory, and I've made a directory called orig micrographs, which contains 1/5 of the micrographs that were provided in the original download. I took every 5 images. So you can see they're numbered 0, 5, 10, 15, etc. Now this data, if you look at the paper, was collected on a Titan Krios equipped with an energy filter and a K2 camera, Gatan K2 camera. And the Gatan K2 camera was being operated in super resolution mode, meaning you get 2 pixels out for every, actually 4 pixels out for every physical pixel on the detector. The resolution is twice as high as the physical pixels on the detector. It does this by counting and then finding where each electron impacted with more precision. Now, most of the data in the super resolution regime doesn't really gain you all that much. And since those images are huge, they're almost 8K by 8K. Again, since this is a sort of a rapid demo, what I want to do is I want to downsample that data immediately by a factor of 2, and then that data will be a little bit easier to work with. That means the angstrom per pixel value will be larger, and the resolution we'll be able to achieve won't be quite as great, but it should be fine for this demonstration. So if I run E2 display just quickly here, and don't worry, I'm going to do a little bit more summary about EMAN2.1 and stuff in a couple of minutes. I just want to get some processing started here before we move on to that. So again, what we're looking at here is my Linux desktop computer displayed remotely, and I've got it set up using virtual GL in addition to Turbo VNC, which gives us access to OpenGL graphics display remotely. There are a variety of ways you can accomplish the same thing, but this one works pretty well. So if I look here using the EMAN browser, I just said E2 display opens up the browser window. I can click here and I can see that each of these images is 7,676 by 7,420 pixels. Now I'd like to shrink those all down by a factor of 2. We can just look at one of these quickly to sort of see what it looks like. Oh, and you can see I'm getting an error message about the GLX extension missing on display 1.0. That's because I forgot to start up the OpenGL emulation layer. And to do that, I have to do VGL run, VGL run, ZSH, and now this new shell should give us OpenGL display. So we'll run E2 display again. And I'm sort of assuming that you're familiar with some of the basics of using EMAN2 here. I've got 3 other Hangouts on air where I've shown people, given people an introduction to how to use various elements of the GUI. So if you find any of this really confusing, please watch one of those earlier videos. I will take my time today, but I'm not going to re-explain everything that we've talked about before. Okay. So now I can do show 2D, and I can actually see the image. This is at a very high resolution here. I will zoom out a little bit so we can see more of the micrograph. I'm using the mouse wheel to do that. And we can see that density in the background. Those are the beta-galactosidase particles. Some of them are aggregated, some of them are nicely isolated. It just varies. If I middle click again, I can get my control panel, and I can play with the contrast. The contrast is already pretty good. I could try maybe this. That may enhance things a little bit. Let us see a little bit better. Anyway, we can see that there are very clearly particles in here. They're not perfectly monodispersed, but there are a number of particles that are reasonably distributed on the image. So at a first glance, I would say this data would be okay to proceed with processing. Okay, so the next thing I want to do is I want to shrink all of the data by a factor of 2. That's going to take a couple of minutes, so I'll get that started, and then we'll go and look at a couple of other things while that's happening. So I'm going to use the e2proc2d.py command. I'm going to use the new wildcard capability that was added by Vernon in my group recently. Let me go into the original micrographs directory to do this. So I'm going to say e2proc2d.py star mrc, and I'm just going to put the output files in this same original micrographs directory for now. So we'll just say @sign.hdf. So I'm going to convert them from from MRC to HDF format while I'm doing this. They don't have to be in HDF format for the next step after this, but that way I'm not destroying my original images, and I can easily differentiate them by file name, so it's convenient. And I'm going to say -- median shrink equals, or just 2. The equal sign here is optional. Just say space 2 as well, and sometimes that's more convenient. Now, there are 2 ways of shrinking your data here. There's median shrink and mean shrink. As you might guess based on the name, if you say mean shrink 2, it will take a 2x2 box of pixels and average the values. If you say median shrink 2, it will take a 2x2 box and will take the median value. The advantage of median here is it will do a better job of eliminating outliers. So if you have, say, an X-ray pixel, which has got a very, very high value in one particular pixel, it will tend to help filter those out. Now, we have other mechanisms for filtering those out later as well, so it's not critical. This just has slightly different statistical properties, so I'll do it this time. But you could equally well use mean shrink. Now, I'm not doing any low-pass filtration of this data before I do this averaging process, which means some of the high-resolution signal present in these micrographs past half Nyquist, past at the highest resolution information, some of that information may get aliased back into my image if I don't do any low-pass filtering as part of this process. The median shrink will have a little impact on that, and for purposes of what we're doing right now, it's fine. It's not necessary to do anymore. So I'm going to start that, and that's going to take a little while. You can see each image is taking about a second because it has to read we're reading 220 gigs of data. So while that's going on, let me go back here and just give you a little introduction to EMAN2.1. Here is a list of a few of the most important changes we've had in EMAN2.1 since the EMAN 2.0. The biggest change is we've gotten rid of the BDB system. In EMAN 2.0, lots and lots of people were frustrated by this BDB database system we were using to store both image data and metadata information about the projects. So we've basically eliminated that. You can still read old BDB files. We haven't eliminated support from the system, but the project management system, nothing will use it by default anymore in EMAN 2, in EMAN 2.1. Sparks, which is also downloaded when you get EMAN 2, still uses BDB for a lot of things, and I've been pressuring Powell a little bit to maybe try and switch back to HDF files again. We actually wanted to use these HDF files originally when we made EMAN 2, but at the time, HDF had some performance issues. It couldn't store large numbers of particles very efficiently, and it took them about 3 years before they managed to resolve those problems. So in the meantime, we had to do something, so we used this BDB system, which proved, I would say, in retrospect, to be a mistake. Now, all of the image data is stored in these HDF files by default. You can convert to any other file format you like. HDF files are just flat binary files which you can rename, move around. You don't have to worry about all the problems that you had to with BDB. And all of the metadata, the information about these files, are stored either in the header of the image file itself or in human-readable text files in a format called JSON. It's a very readable, editable format that people can look at. You can also use the browser to look at the contents of those files, but you can also just use a text editor and look at them too. This is a big improvement. We now use the gold standard refinement for all refinements. You no longer do you have to run a refinement and then when you're done, run another program to find out the resolution of your structure. Now it splits the data into two halves at the very beginning of the processing. It does the refinements of the even and odd halves completely independently, including using different starting models for the two halves. And this means that every cycle of refinement, we have a true resolution value which isn't subject to initial model bias or to noise bias. Now, you may still have noise bias going on. This is sort of an important distinction Nico Grigoriev raised last week at Bridget Carragher's meeting at the NRAM. Yes, you may still have some noise bias going on, but it won't influence your resolution value. And when you filter your data, we filter the data based on the resolution value, which is computed by comparing these two independent halves. So any of that noise bias that's getting into your data should be basically getting filtered out in any case. And if you look at the even and the odd models separately, you can tell how they differ from one another. In general, EMAN2.1 is about 10 to 20 times faster than Relion, and we have now demonstrated in several cases that you can get basically exactly the same structure out of EMAN2 as Relion. Now, I say basically exactly the same structure. If you compare any two structures computed with any two software packages, they won't look absolutely identical. The image processing that's used in the different packages is different. And if you have things like heterogeneity, or anything like that, the different software packages will handle that differently. But the resolution you get out in EMAN and Relion, and in most cases Freeline as well, is basically identical between the two packages. There are caveats there, with how you mask the data, that sort of thing. We'll talk about that later on in the process. But basically, you can get exactly the same structures out, and you can use a lot less CPU time doing it. If someone were trying to use EMAN 2.0, I would say that, yes, what Shores has done recently to make Relion easy to use, EMAN 2.0 was kind of a pain to do a bunch of things in. I think in EMAN 2.1, it's sort of a completely new package now. It's very streamlined. It does force you to actually look at some of your data and not just process it completely blindly. But beyond that fact, I think it should be just as easy to use as Relion is. And actually make you consider what you're doing when you're doing your processing. We have also added interconversion from Relion, from EMAN 2.1 into and back from Relion, Freeline. If you like the CTF parameters provided by CTFind, you can use those instead of EMAN's fitting. And we also providing interconversion to the EMX format, which is in the future should allow you to interchange your data between EMAN 2.1 and other software packages without us having to write a specialized converter for each package. So if you want to try your refinement in EMAN and then convert it to Relion and see what Relion does, you can do that. If you do a refinement in Relion and you want to see what EMAN2 does, you can take that and you can import it back into EMAN2. We're trying to make things as flexible as possible. We have, I would still consider this sort of beta level, but we have software in EMAN 2.1 for movie mode alignments of both whole frames and per particle alignment. And the per particle alignment is somewhat similar to what Shores is calling particle polishing in Relion. These have been tested and they work on several projects, but with any of the movie mode alignment software in any of the software packages right now, I would say that it's not guaranteed that it's going to work in every project. All of these software packages have been tested in a somewhat limited number of cases, and you'll have to sort of see how they look at your data results with a critical eye if you're going to use them. There's a complete single particle tomography, also known as subtomogram averaging system in EMAN 2.1, thanks to my grad student who's now graduated and is now a WAS postdoc, Jesus Montoya. We have a much easier particle set management system, and you'll see that as we go through here. Tilt validation is supported. We've added a bunch of new file formats to support direct detectors, that sort of thing. and there's a bunch of other additions as well. Now, I'm sure that the shrinking process was completed a long time ago, so let's shift back to that and see where things stand. So now if we look in this directory, you can see it finished running my proc2d command. We'll see I have a whole bunch of HDF files as well as MRC files. If I run E2 display again, we'll see that the MRC files have twice the dimensions of the HDF files. If I open up one of these HDF files, we can see that I don't have to zoom out nearly as far before I start seeing the beta-galactosidase particles floating around in ice. So the next thing we need to do is actually import this data into the system and do some initial CTF determinations on it. So I'm going to run E2 Project Manager, which is the main interface that you'll use in going through projects where if you want to be guided by the graphical interface. Now, the first thing you do when you start a new project is go into the project menu, edit the project, and enter some of the parameters. In this case, well, the mass is actually somewhere around a half a megadalton. You don't actually have to have a precise mass value in there. This is interpreted somewhat loosely anyway. Maybe I'll say 450 here. It doesn't make a big difference. The C sub S, so this data was collected on a Krios, which should have a C sub S of 2.7 millimeters. Voltage is 300, and the angstrom per pixel value we need. Now, when I downloaded this data from the data bank, I got another file as well. Now I just messed up. I ran the project manager from inside my micrographs directory. So what I need to do now is quit the project manager. I'll go ahead and just say OK. I'll edit this again in a second. Quit the project manager, and this caused the creation of this info directory here. I want that info directory to be up one level from where I am. So I'm going to do move info period. And now we'll see I've got the info directory back in the root folder where the micrographs folder is. So let me run E2 Project Manager again and edit my project again. And now we can see I need to make my decision about the angstrom per pixel value. Now you can see there's this other XML file here. This also was downloaded as part of the download of the micrograph data. If I use my file browser, I'll cancel this out. I'll use the file browser. I should be able to see that XML file. And if I say info, that's right. So I don't have any special class set up for XML files right now. I was hoping it would show me a text editor, but we'll just have to cat it here. So if we look at this text file, we'll see down here at the bottom it has pixel width. So that should be the angstrom per pixel value for the data. And luckily it's the same for both X and Y, which you pretty much expect. So the raw data should be 0.6375 angstroms per pixel. Since I shrunk the data by 2, it's no longer 6.375, and we'll need to enter that value. So we'll go back to the project manager again. Edit the project, and now we can enter the angstrom per pixel value, which is 1.275. Okay, now the next thing I need to do is basically we're going to go through these steps one at a time. You can see we're already 20 minutes in and we haven't even really done anything with our data yet. It's okay, we won't get all that far today, it's all right. So there are two choices here. I can say evaluate and import micrographs, and that'll open up an interactive display where I can look at each micrograph and decide whether I want to import it to the project and do some initial CTF estimation, or I can just say import micrographs and import everything into the project, and then if I want I can go back and look at them later. So I'm just going to do this all in one step, and that'll do the initial CTF estimation as well. So I can say import micrographs. I'll hit the browse button. I'll need to go to the original micrographs directory, and you can see I have both the HDF and MRC files here. I don't want to import both sets. So I'll go into the filter window here and I'll type star.hdf and only look at the reduced size ones. Then I'll tell it to select all, OK, and then I have to pick all of my information down here. So all this should be pretty much OK. The default amplitude contrast is 10%. That's usually OK for most projects. Sometimes you set it a little higher. These values should be filled in from the project, and it looks like they're OK. Then I want to invert the image because it was collected on a CCD camera. If you collected the data on film, you might not have to do that, depending on how the film was scanned, but hopefully most people aren't using film anymore. I'll go ahead and do the X-ray pixel filter, even if my median shrinking process probably removed most of them. It's not a bad idea to do that. Edge normalize, that rescales the data, so the edge of the images are 0 and the standard deviation of the images are 1. Unless you need to look at the raw pixel values, that's also a good idea. And I'll tell it to do an initial CTF estimation from the whole micrograph. I can also tell it to estimate the astigmatism, but my normal process is to not do astigmatism on the first pass. I'll go through and do my data processing without astigmatism, and then I'll go back and add it later on once I know I've got all the process right. That's just a sort of matter of choice. Okay, so now we can see it's taking about 1 second per micrograph to do the defocus estimation and import it into the project. So let's go and talk a little bit more while this is going on. I had one more slide about EMAN2.1, and these are things which I had hoped to get into 2.1, but we didn't quite have enough time to finish before we really needed to get the 2.1 release out. So one thing we don't have in there yet is the new particle picker. So the particle picker that we've got in there works reasonably well for interactive picking, but if you have 2,000 or 3,000 micrographs, it's not a very efficient way of going. Now, Paul Penchek, in his Sparks package, which is distributed with EMAN2.1, has a command line variant of the automatic picker, which uses a Gaussian mechanism for automatically picking particles and works pretty well. You can go to the Sparks web page and get information on that. We're also going to be revising this over the next couple of months and hopefully getting a better particle picker in sometime pretty soon. The file browser in EMAN 2.1 is a little slow if you have really large projects. And this is really so we rewrote the file browser maybe a year ago, something like that. We made it much faster, and it was terrific, and everything was fine. But then we had to take sorting based on columns into account. And when we added the sorting, it got really slow for large projects. If you have under, say, 1,000 or under 500 micrographs, it's fine. It's a little bit sluggish when you do certain things, but it's still quite usable. If you have 2,000 or 3,000 or 4,000 micrographs in your project, or 10,000 micrographs in your project, it's pretty slow. There are a few tricks you can do to make it a little bit faster, but this is something that we also need to work on. I've started designing the new browser, which will not have the problem of speed with really large projects, but it's not quite done yet. And then finally, there's a program for computing variance maps using the bootstrapping method that Paul Penchek wrote a paper on some years back called E2 Refine Variance. And we just discovered a few days ago that that's actually broken. No one had fixed it for the new stuff in EMAN 2.1, and it's going to take a little bit of effort to fix. So it's not fixed yet. So hopefully all of this stuff will be in the next minor 2.1.1 release or something like that, and we'll be ready to go. Okay, let's see how our importing process is going. It looks like it's done. So now we can go. Now I'm going to go ahead and do evaluated import micrographs. Even though I've already imported them, I'm just going to pick a few of them and look at them and make sure the automatic fitting worked right and everything's okay. So we'll say browse, and now I have a micrographs directory where the imported micrographs live. These are really just a copy of the other files. Nothing special has been done to them. So I'll pick maybe the first, I don't know, say 15 of these, and we'll launch them into this evaluation tool. Okay, now we open a whole bunch of windows here. Okay, one window has the micrograph itself. There's another window that popped up, I think, behind that window. Let's see, I've got, oh no, there it is, it's right there. Okay, so I've got a window here showing the entire micrograph. I'm going to move that over here. And this is a little sluggish again because I'm displaying remotely from my Linux box. At the same time, this presentation is being broadcast to Google. At the same time, it's being recorded on my laptop computer using ScreenFlow. So we're going to have some sluggish graphics going on here, but it'll be okay. So the green boxes you see here are the regions that it boxed out for determining the CTF. If I look down here in this plot window, I'm going to make this a little bit bigger just so we can see it better. What we're seeing is the CTF fit. Now you're not seeing very much here. If I use the right mouse button and drag a box, I can make it a little bit bigger, and now we can see the CTF fitting based on the whole micrograph. Now, this CTF fitting will not tell you the quality of your particle data. It will tell you the quality of the micrograph as a whole. If you have a continuous carbon film sitting behind your particles, or if you have a lot of stuff floating around in the buffer, which causes contrast, even if your ice is too thick, you can still get a very nice curve here. And that'll tell you the defocus, and it'll tell you that the microscope is performing well and giving a signal out to 4 angstroms, that sort of thing. But it's not telling us how much contrast we actually have in the particle data. That we're going to get later after we box out the particles, and that's actually a very important point. But at least we can see that we've got very nice signal extending out to at least 4 or 5 angstroms here. And we can also see, so the black curve is computed from the micrograph. The blue curve is a fit curve based on theoretical CTF, standard CTF theory in cryo, using the weak phase approximation. If I go through these micrographs one at a time, now note, it's okay, I could have actually opened up all the micrographs in the project here. It doesn't actually read the data into the memory of the computer until you click on the micrograph here, and it only loads one at a time. So you can load as many as you want up into this program, and it won't make your computer crash or anything like that. And if we go through these one at a time, we can see that looks like the automatic fitting worked reasonably well in most cases. Oh, look, see this one, it didn't work perfectly. And if we run into a situation like that, we need to just adjust it roughly and then hit the refit button and get it straightened out. So there may be a couple of others like that since we saw one. In most of these automatic fitting routines, now if we look here, for example, this one where it looks, oh look, it's off a little bit, you probably don't have to worry about that one too much. When it does when it fine-tunes the fitting later, it'll take care of any little defocus errors there. But if you have an error where the first zero is just completely out of place, then that's something you'd probably want to fix if you see it. Okay. So it looks like it did a fine job, and always when you do this sort of processing, you'll have some percentage of them which will get fit incorrectly. In this case, yeah, actually, I don't know. I'm not sure. Oh, I can see it. It just got really low here. All right, so it looks like everything's okay. I was also looking at the micrographs over here while I was going. It looks like the particle density is a little too high in some of them, but in general, there are particles there. There's data that we'll be able to process. It may take a little bit of work to get only the isolated particles so we can get to high resolution, but in theory, it should all be feasible. Now, this window by default is showing a background subtracted power spectrum. There's another window here which shows us the two-dimensional version of the power spectrum, along with the bluish lines, which are showing us the positions of the zeros, the CTF. I can turn off that annotation if I wanted to see the raw power spectrum. And you can see very nicely, we can actually see these ripples extending out to pretty high resolution here, which we also see in this one-dimensional curve here. And if I want to change what's in the plot, I can also look at things like the foreground and background curve. Now, if I do this, you'll see something that's just a little funny if you haven't worked with K2 data before, and that's that the background can actually go up in intermediate resolutions. Now, it looks like when they collected this data, they probably collected the data using very long exposures, which means that the electrons per pixel per second was actually quite low. And we're not seeing the sort of anomalous effect that we see in a lot of K2 data, where you actually see the background dipping down and then going way up again before it starts dipping down again. Here, it looks a little bit unusual. It's sort of flat here, but it doesn't really go up very high. So if we look at K2 data from another project, you may actually see that sort of funny effect. But the background subtraction strategy in here takes care of that automatically for you. Use different strategies for background fitting. One strategy, if I uncheck that box, would just be to, let's see if it shows. Now it's already adjusted to fit, so it's not going to unadjust it for me. Is to sort of use a monotonically decreasing curve, and that works really well with data collected on detectors in integration mode, where the background almost always falls off in a somewhat exponential way. But if you have one of these data sets collected in counting mode, you'll find that that doesn't work very well. We need to have this box checked. It's checked by default now, so normally you won't have to worry about it too much. Anyway, we'll go back to the background subtracted curve, which is a lot easier to look at. And again, we have this sharp peak at low resolution due to gradients in the image, so we'll need to zoom in to be able to see anything. All right, I think that's all we really need to talk about here. If I were importing the data by hand, I would hit the import button for each micrograph I decided I liked. Since we've already imported all the data and done the CTF estimation, we don't have to worry about that. Okay, so now we've decided that our micrographs are probably okay. The next thing we need to do is pick particles. Now I'm going to go ahead and do this interactively. This may be a somewhat slow process given the current swarm boxer, so we may not pick all of the micrographs at this point. I'll go ahead and open maybe the first 20, and we'll see how far we get. Okay, so this is going to give us multiple windows opening up on the screen. The first time you run any program in a new project, it just positions the windows somewhat randomly on the screen. Once you reposition them and exit the program, if you launch the program again, it should put them back where you had them the first time you ran the program. So I've got a window here for particle data. This is after I select some particles, it will show them to me there. I've got my thumbnail view, which allows me to pick which image we're boxing at any given moment in time. Then I have the micrograph view, which is where we're going to be clicking on the particles. And that's going to start by default zoomed way out. And then I've got my control panel here. Oops, and of course I click bad place. I've got to bring all my windows back to the front. Oh, did it again. Okay. So let me try one more time. We'll make this window a bit bigger. And then we need to zoom in so we can see the particles for picking. All right. Now the next question we have to ask ourselves is what box size we're going to use. Now you may not know initially how big these particles are. Now most particles that you're going to do cryo-EM on are going to be somewhere in the range of maybe 150 to 300 angstroms in size. Obviously, if you're doing, say, a virus capsid or something like that, it's going to be a lot bigger. But most of the typical small single particles that range in mass from, say, 200 kD up to a few megadaltons are going to be in that general sort of size range. Still, that's a pretty wide range. So we need to decide how big a box we're going to use. So let's pick a nice looking particle. And I'm going to open the control panel here by clicking the middle button. And I'm going to select the Measure tab. And this will allow me to measure how many pixels something is in the image. So I'll drag a box here, and I can see that my particles are about 175 pixels long. Now again, keep in mind, this is the data we've already decimated. We've already shrunk the data by a factor of 2. So in the original images, these would have been some 400 pixels in size almost, 350 pixels in size. We can measure a couple of other particles just to make sure we've got a good estimate. We want to find sort of the longest axis of our particles. And I would say 175 is probably a reasonable value for the longest axis of these particles. So now, how do we decide what box size to use? Picking the right box size is very, very important. It's not only true for EMAN2, it's true in other packages as well, even though they don't always stress it. the speed of the image processing can depend very heavily on the box size you pick. So let me go back to the EMAN2 wiki here. Now there's a very useful page in this wiki, which is file formats, image processing functions, and mathematical conventions. If you don't know anything about symmetry groups, or in this case, the box sizes that we should be using, we go to that page. So there's another page here on particle box size, and this page has a list of all of the good box sizes you can use. If we look down here, there's actually a lot of details. You can see plots. You can see a detailed list of all the different sizes and how we computed this. But basically, you want to use a number, a box size from this list if at all possible. Okay? If you said, oh, I wanted to use a box size of, say, 175, what you would do is you'd go to this list and you'd pick the next larger size. The way this list is constructed, if you have a value smaller than one of these numbers, you will always make the refinement faster by picking the next larger value. There are some cases where if I picked like 194 instead of 196, you could actually make the refinement take 5 times longer than it should if you had picked a good box size. This is mostly about speed. So I suggest always using a size off this list. Now the recommendation for EMAN2 is that you take the longest axis of your particle and multiply it between 1.5 by 1.5, some number between 1.5 and 2 to get the box size that you use. If your particle is really small, it may be okay to go to a factor of 2. In most cases, 1.5 is probably enough. Okay, so if I take 175, we do that 175 times 1.5, and that gives us a size of 262. So we can look at our list here. Now, we're probably cutting it a little bit tight if we use 256, but 256 is actually a very nice box size, so maybe that's a good one to pick. If we don't want to use 256, I would probably go up to, say, 288, something like that. It's a little bit more than 1.5 times, and it's a pretty good size as well. So we'll go ahead and just use 256. So I can close this control panel here now, and I'm going to say box size 256. And by default, when I start the particle picking program, it's in this swarm boxing mode, which is an automatic particle picker. Now you'll note there's 2 sizes here. There's the box size, and then there's the particle diameter. The particle is usually smaller than the box, so the particle diameter gives it some feel for about how big the particle is within the box. Now 175 was my longest axis. Let me try something like 150 to start out with here. So now I'm going to go into my image. I'm going to click on a particle. And it didn't do anything. I'm worried that somehow... Oh, I know I didn't do anything because I had set my display here into measure mode, which uses clicking to measure distances. I need to go back to application mode here. And then I'll get application-specific mouse functions. Silly me. But these are the sorts of gotchas that can get you. So now I'll pick out a particle, and I will normally see immediately it will pick a bunch of other particles. Sometimes it won't happen. Sometimes I need to pick a couple before we see anything. So I'll pick another particle, and eventually we should start seeing additional particles automatically appearing. Oh, there we go. Finally, it started picking a few more things. Now, maybe I need to make this particle size a little bit bigger. There we go. So now it's selecting a few more. So maybe we'll even make it 180. All right, that's probably fine. So I'll pick a couple of more manually, and the idea is we keep trying to pick particles until we're reasonably satisfied with the selection that it's doing. It's never going to be absolutely perfect. It looks to me also like they must have had some gold fiducials in this data. Maybe they were doing some tomography experiments on this on these grids as well, something like that. Obviously, we don't want to get the gold particles mixed in with our actual data if we can avoid it. But automatic pickers do tend to like gold a lot, so we'll have to sort of see how it goes. Now, usually after you click, it'll try and get the center of the particle in the box, but that doesn't always work. You can always manually adjust it afterwards. So I'm going to downscale this data a lot so we can sort of see what we're getting. All right. Now, I don't want to try and do a really careful job of this on my first pass. There are mechanisms we can use to go back and automatically clean up the data to some extent later on. Usually, I would say you don't want to do a really poor job of particle picking. It'll cause you troubles later on, particularly if you're targeting a really high-resolution structure. But in this case, speed is somewhat of an issue because we're not going to be sitting here all day long. So I'll go ahead and move on to the next micrograph now. Now, if we look at the next one, you can see it's very dense. It's actually pretty hard to pick particles which are really well isolated in this set. So I think, honestly, I'm just going to skip this image for now and move on to the next one. Now, this image is really far from focus. It also has a pretty high average density, but it's not quite as bad as the previous image was. At least I can find some particles in here which are reasonably well isolated. Now, if I continue to pick particles using the swarm mode picker, it will continue to update my selection, the automatic selection as well. If I want to just add a few manual boxes to a particular image without influencing the automatic picking, I can go over here and change the boxing tool to manual. And then if I pick a particle like this one, it'll be white instead of black, and it won't influence the automatic picking. Okay? At this point in time, I don't really care too much whether I'm getting really good results, so I'm just going to move on to the next one here, and we'll just use the ones that it automatically picked. These images that we're looking at here, these last couple, have been so far from focus, probably we're not going to end up using them anyway for a high-resolution map, but we'll see. We haven't really made that decision yet. So I can go through here and I can manually pick out particles which are nicely isolated. I could manually go through and delete particles which aren't nicely isolated. But I think for the sake of argument, we're just going to sort of pick stuff and see what happens this first time. Okay, so I'm not going to do a super careful job at picking, and we can sort of see how the refinement process works out. Okay. So I want to get at least these first 10 picked out quickly. Okay, so I'm just going to use the auto boxing for the rest of these images here. This, you can see, is a very close to focus image, and we're not getting very many particles, even though there are probably a fair number of particles in this image that we can, you can see them fairly faintly. The question is whether I want to spend a lot of time right now getting this one to work out well. Probably not, so I'm just going to move on. Now, sometimes you will find areas of strong ice density, like here, getting picked as if it were particles. This is not a good thing. Having particles which are bumping up against other particles, that's not terrific, but it's not necessarily going to be super destructive. This can cause us a lot of problems. So I'm going to hold down the Shift key to get rid of boxes, and I'm going to manually erase the boxes that are infringing on some of this bad ice. So you can delete boxes that way which are automatically picked or manually picked. And hopefully they won't come back again. In theory, once I've marked a region of the image as bad that way, it won't bring them back again later. Okay. So again, I'm just going to go through and basically trigger automatic picking on these images by selecting them. And we won't worry too much about particle quality or getting all the particles. You can see it's only picking a few particles from each image this way, and there's a lot more present there. We'll need to go back and do a somewhat more careful job if we're going to really process this data properly. Now we can see this image, if we zoom out a bit, actually you can see it in the thumbnail there, actually has a pretty strong ice gradient in it. That's not necessarily a problem, and in fact, a lot of people actually collect their data so they intentionally have a gradient in the image, and at the thin end of the gradient you don't see any particles, and at the thick end of the gradient you see a lot of particles, and then you know that the ice density in the intermediate region is pretty good. down to the last 15 minutes or so of what we're going to do today. Let me go and see. People may have been asking questions. Maybe not. I don't know. But let's take a look and see if there are any questions there. Okay. Haven't had any questions. Good. I didn't miss anything. All right. Let's finish this up really quick. Yeah, this probably isn't a terrific image. All right, so I've got my first 20 particles at least vaguely boxed out now. And I'm going to go ahead and get rid of some of this obvious noise. A little bit more. Oh, no, maybe not. That's about it. All right. Now I can exit E2 Boxer. And maybe what I'll do is I'll launch E2 Boxer again, and I'll do a few more of the micrographs that way, just in that very rough way. So I'll pick. So you can see now in my list, I can see how many stored boxes there are for each of these images. In other words, how many particles it automatically picked already. So now I'll go ahead and down here, and I'll pick, say, we'll go ahead and do the next 20, and get some rough boxing done on those. When I hit launch this time, you should see, once it's loaded all the thumbnails and stuff, it rearranges the windows. You'll have to zoom in on this window still, but other than that, it should have kept the windows in a decent location. All right. Now, what we see happening here is that Swarm has basically reset itself. I didn't load any of the images that had already been Swarm boxed, so I don't have any parameters. So I'm going to have to manually pick a few of the particles again. My parameters are the same here. The 256 came through, although this I needed to set back to something like 180. So let's pick a few templates again here. And you want to pick particles that have somewhat diverse appearance. You can see when I added that box, it actually got rid of a bunch of the auto-pick particles. So adding sometimes can make fewer particles be picked as well as more particles be picked. That looks like a pretty decent arrangement. I mean, it's not a lot of particles per frame. We're missing a lot of it, but it's not too bad. Okay, so now let me go back to this one. I didn't do my manual picking here because I knew this was going to pick a bunch of junk that it shouldn't get. Now, this image has lower contrast, so it looks like it's not picking up. Swarm isn't picking up too much other than that strong contrasty ice. So maybe I'll go ahead and add a couple more references here. And again, I want to get rid of some of this stuff on the contamination. Now, if you use some other automatic picker, you could also go back and you could use this tool to sort of clean up the bad images from a standalone auto picker too. However, there are probably better ways of getting rid of outliers, bad particles, that sort of thing. And we'll see that once we really start doing some processing, which looks like probably won't be today. Not sure if I need to do all 20 of these. I think we may just want to move on here. At least I'm getting a few particles from each frame, which give me enough to do more work with the contrast transfer function. So the minimum number of particles that we need for particle-based CTF determination is about 15 particles per frame, typically, 10 or 15 particles per frame. If the particles are really big, like virus particles, you may be able to get away with only 4 or 5. But for smaller things, usually you need at least 10 or 15. Okay, let's just, there, that's probably good enough for today. Now, next thing I'm going to do is I'm going to go ahead and do a generate output. So I've picked where the particles are, but I haven't actually saved the boxed out particles to separate stacks. I'll enter my box size of 256, and I'll go to my list, and I'll click on the stored boxes so I can sort it by that, and I'll only pick micrographs where we've got at least, say, 20 particles. Okay, I shouldn't really have to pick any of these other options. It should all be, the default value should be fine, and I can hit launch. And now it's going to generate files that contain stacks of boxed out particles. If I open up this window, I can see the progress as it runs, but it's already done. So, okay, the next thing I want to do is go into the CTF and do automatic fitting. Now, I can just click all particles here, in which case it will look in the particles directory. And here we can do that ourselves. If we look in the particles directory, we'll see now we have all these stacks of boxed out particles. It'll look in the particles directory and process all of the images there, limited by some of the values that I put in here. So I can specify, oh, actually, sorry, at this step, we don't limit it. If you say all particles, it'll do the fitting on all the particles. If I don't say all particles, then I have to go to the browser and I have to pick which ones I want it to work on. Let's see. I can put a couple of limits in. I can specify the minimum number of particles that should be in the image. So it'll ignore any images. If I type 20 here, it would ignore any images and particles that don't have at least 20 particles. And I can also filter based on quality. So the quality is a purely human set value. It normally defaults to 5. So if you have a really good image or really bad image, you can manually identify those for selection later on. Now, I usually want to do some oversampling. What that'll do is it'll take each particle and expand it by a factor of 2 for processing, for computing the CTF. And it'll make the CTF curves a little bit smoother for fitting. This is most important if you're fairly far from focus. If your images are all, this isn't as big a factor. Or if you have a very small box size, that's important. All these other values in here should be correct. And in this case, I'm going to use the default boxes again here. I'm going to tell it to do an automatic high-pass filter, which gets rid of that really sharp peak you sometimes see at very, very low resolution. I'm going to tell it to fit. If you don't check that, it doesn't do any fitting. And I'm going to say curve defocus hint. That'll use the defocuses that it determined on the whole micrograph as a hint for the value that it determines here in the per particle basis. Now, there's actually a reason to allow the values to change. You'd say, well, the whole micrograph defocus value should be better. That's true, and it's not true. The whole micrograph value is based on everything that it sees in the image. That could be the thick carbon film on the edge. That could be the continuous carbon substrate if you have one of those. It's not necessarily just the particles. In this case, we're fitting the defocus based on the particles themselves. And there are cases where that can actually give you different numbers. Now, it's not going to be different enough in most cases to matter at 15 angstroms or probably even 10 angstroms. But if you're trying to push down to 3 to 5 angstroms, you may reach the territory where some of that has an effect. And again, I'm going to skip astigmatism for now. And I don't think we need any of these other parameters right now. Okay. If you'd like, you can also specify constant B factor. The B factor fitting that it does automatically is very coarse. In some projects it works well, in other projects it doesn't. It's not used for anything. You don't have to have a good B factor in there, but when you're looking at the quality of fits, sometimes it can be useful. And I can also specify multiple threads. I actually have 16 cores on this workstation, so I'll say 16, and then I'll make the fitting go much faster. So we can see it ran 16 processes. Oh, it's already done. Okay, so it's already done all the CTF fitting. Now I can run interactive tuning, and I can see I now have defocus values, B factors, everything for all of my particles. So again, I'm just going to say all particles, and I'm going to check sort defocus. that will load all of the particles that we have CTF information for and sort them in order of defocus so that it's easier to look through them in an organized fashion. And again, we're almost at 11 o'clock now, so we're going to cut this off pretty soon. Okay, now this again will open a number of windows. Again, we have a 2D CTF view and our 1D plot, but again, now it's based on particle information instead of being based on whole micrograph information. Now, if I zoom in here and look at this, you can see the curve is noisier. That's because it's based on particles, and there weren't that many particles in a lot of these frames. If we look up here, we can see we had 33 particles in this frame. So in this case, the fitting probably was better on the whole micrograph basis just because we don't have a lot of particles. Now, if we go back and do a careful job and box out a lot more particles, this curve will become a little bit smoother. Now, this defocus is about 1 micron, and I can go through these one at a time. And we can see we're going gradually up from 1 micron to higher defocus values. You can see some of these curves are very smooth. If we look up here, though, we see we had 215 particles in this image, so it's based on a lot more data. If I look in this window, what it's showing me isn't a particle. This is showing me the average of the first 20 particles in that file. If I use the up arrow, I can look at those individual 20 particles. Now, it doesn't load all of them, it just loads the first 20. And then the average is just giving you an idea of how well centered the particles are and how much junk you have in the ice outside the particles, which is actually an important factor when it's determining the CTF the way EMAN does. I'll tell you more about that next time. So I'll just go through here, and we can see that it looks like we've got pretty reasonable defocus values for all of these images. It's not perfect. You'll note that at low resolution, we don't have a perfect fit. That's because we have structure factor. This is due to the shape of the particle itself, which hasn't been taken into account yet. So now that I know I have decent CTF parameters, I'll exit this program, and I'll say generate structure factor. And what this is going to do is it's going to look through all of the CTF fits that you've done and try and come up with a simultaneous structure factor which would satisfy all of those CTF curves optimally. So I'll just say launch here. We can see some output coming out on the screen as this runs. And this will run for a maximum of 7,000 or 8,000 maybe iterations before it stops. And it's gradually improving the quality of our structure factor. Okay, once it's finished running, I can go back to interactive tuning and take a look at my fits now. I could actually go back and do automatic fitting one more time. Now that we have a structure factor, it may actually improve the fitting in some cases. The false positive, the bad answers we were getting when we did the whole micrograph fitting, a lot of that was based on not having structure factor information. So in fact, if I go back and I redo the automatic fitting with the structure factor, and I turn off the current defocus hint option, I would probably get completely accurate fits, or at least a lot more accurate fits of those outlying micrographs that didn't work perfectly the first time. Anyway, I'm just going to go back to interactive tuning here because we're going to wrap things up here. And now we should see that our fits at low resolution in particular should look a lot better. Now they're still not going to be perfect. And that's because we have different orientation distributions in the different micrographs. It may also be that the structure factor that we determined here isn't absolutely optimal because I was basing it on a lot of images that had a small number of particles in them. So we can see this image, which had a fairly large number of particles in it, the fit's actually a bit better at low resolution. A lot of that we can actually fix by just tweaking the B factor a little bit. So here I can actually make that match a lot more nicely by just playing with the B factor. Now, part of that is because the actual envelope function of the microscope detector combination isn't really Gaussian. It's kind of Gaussian, and at low resolution it's pretty Gaussian, but once you get out to high resolution, it's not really a true Gaussian anymore. So trying to fit it perfectly with just this standard B factor is never going to work absolutely. Now you'll also note there's another curve in here, this dotted curve. This dotted curve is the background is the CTF that you would have gotten if you did the background subtraction using a mechanism that doesn't take the particle-free background of the images, or it doesn't take the edge of the images into account. I haven't explained all that in detail this time. Since we're sort of out of time, I think we'll hold off on that until the next session. Let me take another look and see if we got any questions. Guess we probably didn't. Oh, yes, there was a question. It said test. All right, well, I don't have an answer for the test question, aside from the fact that I got the question. Let's see, anything else we want to do here? The next thing I wanted to show you will probably take about 10 minutes, so I think we'll just hold off on that until the next session. So we've gotten through our initial CTF determination today, and it may be that offline I will go back and do a more careful job of picking particles from the micrographs, so we don't have to sit through that in the next little demonstration. Next week is Thanksgiving in the United States anyway, so it's a holiday, so I probably won't do another one of these sessions until a week from next Thursday. Hopefully everyone will still remember what it is we're doing and where we are. So I think that's about it for today. Take one last look here. Yeah. All right. So I think we'll go ahead and finish up for the day. I will have this archived online on Google sometime pretty soon. I will probably use the archive that the better archive I got by recording from my laptop rather than the automatic archive. But we'll see how things turned out. Thanks for joining, and hope everyone joins again next time.